Good morning, everyone, and welcome to Amplifying the Unreal Audio Engine with extensions and plugins. This talk is about how to squeeze as much juice as possible out of the Unreal Audio Engine and customize it to your game or your interactive experience. So I'm Jay, I'm Tech Director at SweejTech, where we develop boutique audio technologies that enable teams to implement and deliver world-class audio. And we are Alvin, Alex, Conrad, Gustav, myself, Pete, and Steve. We're also part of Sweet Justice Sound, which means we get to work with the amazing cadre of sound designers there, and we are really privileged to work on so many awesome projects alongside them. So today I'm going to break this talk about amplifying Unreal Audio into three parts. First, I'll go over why we think Unreal Audio is so amplifiable. Then we'll look at how we've made use of this power at SweejTech in work that we've already released, and this will be the main bulk of the talk. And finally, I'll cover what we're currently investigating and exploring. So I hope you take away from this talk a sense of the opportunities you have to customize and soup up Unreal Audio with some concrete examples of things that worked for us and also some stuff that didn't work out and why it didn't work out. I also hope you're inspired to try to improve your workflows and tools and that this sparks some creativity for you and your team. First up, why? So first and foremost, we really like the paradigm of UE audio, the fact that it's centered around node-based sound design. And of course, MetaSounds is a power tool for sound design, and it gives you such flexibility to create interactive sound objects and make them work and sound the way you want them to. So also several folks at SweejTech have experience working in a similar node-based paradigm in a previous company life using an in-house engine, and this kind of gave us the confidence and some of the knowledge to create amazing sounding games using this. With Unreal Audio, you can kind of go from simplicity to complexity with the range of tools and ways to play sound that Unreal Audio offers. So a key part of the system for me is that you can just play WAVs if you want to. They are sound assets when you import them in the same way that a MetaSound is a sound asset, and the system treats them in the same way at a fundamental level. So because of this, you can prototype and work quickly if you need to by just throwing WAV files in. And then while your project grows and scales, you can handle that increase in complexity with more complex asset types like MetaSound sources and patches and that kind of thing. The engine is highly extensible. So this means it's been designed and engineered to allow you great creative and technical freedom to integrate your ideas and your preferences and your workflows into what has already been built. It provides a great suite of default functionality, which is definitely enough to get the project off the ground and into production. But part of the genius of this extensibility that I talked about is how it allows you to override the built-in functionality in some cases and just provide your own. So this means if you have differing needs to what the engine provides, you're not fighting the system. You're only limited by what you can imagine and the amount of engineering time you can devote to what you can imagine. So why should you, as audio professionals, extend the Unreal Audio Engine? There are always going to be specific requirements for each project for audio. So things are going to be different between first and third person games, shooters and action adventures, racing, puzzle games, whatever. And within these genres, individual titles will have things they want to focus on specifically and push the boundaries for. And with the best will in the world, there's no single audio engine that could support all these different requirements out of the box. And that's where the extensibility that I talked about comes in. So it allows you to leverage the hard work of the engine team that build these very solid foundations and some really powerful tools that go on top of that, whilst also taking the whole thing in your own direction. We're all different, and our brains work in their own unique and amazing and weird ways, and because of this, we all prefer different workflows when we're working. So customizing an existing workflow to our needs or creating a totally custom flow pretty much always improves iteration time, and when we can iterate faster, we can get to better sounding things. And I know the UE audio team is packed with world experts making cutting-edge audio tech, but they can't be everywhere all at once. And the engine allows you to bring your own specialized experience to the table for your project. And finally, you might be working on a platform or a piece of hardware that the engine has not been able to extract the most out of yet. And extending gives you the opportunity to plug things together in a way that might not have been explored yet, or might be really project-specific and in fact not appropriate to go in the engine. And overall, it just feels like an audio programmer's playground to me. There's so much of the engine is accessible and overrideable. It's just great fun to work with as an audio programmer. So on to then who can do this who can extend the Unreal Audio Engine. So like everything game dev related, you need programmers for a lot of this stuff. And when I say programmers, I mean people comfortable working with C++. You don't necessarily have to be like a battle-hardened DSP engineer to do this. since many of the extension points are really self-contained and allow you to be very specific about what you're doing without having to scaffold too much around it. Technical sound designers who don't code can also do a huge amount with blueprints and, of course, with MetaSounds. And in blueprints, whether it be by extending existing structures that are already there, hooking into engine delegates, or using editor utility blueprints and widgets to create workflows within the editor. And in my experience as well, non-technical sound designers are usually itching to create workflows and engine behavior extensions, but they don't always have the knowledge or the confidence of how to implement them. And this is where collaboration really kicks into overdrive. And when audio programmers and technical sound designers can find ways to empower sound designers to create the things they need, that's where the magic really happens. So now we're going to look at how SweejTech have approached using these extension points and tell some development stories about our process for using them. We already have several plugins that vary in size and scope, including the Audio Inspector, which has now thankfully been largely superseded by Audio Insights. But this was our kind of first step towards getting towards that, and now Audio Insights is starting to surpass it, which is awesome. So, cool. But we released that a little while ago. There's our HDR, High Dynamic Range mixing plugin, ambience, and we also have a bunch of utility and experimental plugins that we're working with. And something they all have in common is their usage of the engine's extensibility. So we'll take a look at these three plugins along the timeline of when SweejTech released them. And first up, the Audio Inspector, briefly. So the Audio Inspector is a plugin that shows details of the active sounds playing in Unreal Audio Engine at a glance within the editor. I've already talked quite a lot in detail about this plugin and how we made use of the editor's UI extensibility at Unreal Fest 23 in a talk called Building the Audio Inspector. So if you want more detail, please check out that talk online in the Unreal community. But it's still, I think, extremely worthwhile talking about extending the editor in the context of this talk because it's the primary tool we have to create and customize workflows. So Unreal's native C++ UI system is called Slate. It's a very powerful state-based UI system, and I think if you don't get stuck into it, you're probably leaving something on the table workflow-wise. And like many UI systems, it's hierarchical. So widgets are the self-contained unit of rendering and logic, and all the things you see here are at some point widgets. And windows in UE, that whole thing is a window, can host any type of widget. And widgets can also host any type of widget, which allows you to make more or less whatever you can design because you can structure things in whatever way you want. It's widgets all the way down. And right at the bottom of the chain, there are leaf widgets, which know how to render themselves, and they allow you to do custom drawings. So anything that's rendering text is a leaf widget. Any of the pictures are leaf widgets, just how you arrange them on the page and how you feed them data. There are lots of pre-made and layout and functional widget types, so it's worth checking out whether something already exists in the engine before trying to make it yourself, since there probably already is something like it. And there's also a bunch of audio-specific widgets that you can use to make nice, familiar audio-looking tools if you're into that. UMG widgets are blueprint wrappers around Slate widgets. So you can use these to make editor utility widgets from. And anything that can be made with UMG can be made in Slate. So it means that UMG is a really powerful prototyping tool as well for stuff you then want to bake down into code in Slate. Unfortunately, you can't go the other way around unless you provide your own wrapper around a Slate widget for UMG, which is a good way to do things. And if you have something that's kind of reusable, you can put a UMG wrapper around it and use it elsewhere. So that was really brief, but that's the Audio Inspector and how we made it. And now let's look at our HDR plugin. So first off, I want to talk about what I mean by HDR, or High Dynamic Range. So in our case, it's a loudness-based dynamic mixer where sounds are individually metered at runtime and mixed based on some simple rules around their metered values and the system as a whole. And conceptually, it's designed to mimic the stapedius reflex in your ears, which happens when they start to detect that a loud sound might cause your ears some damage, and they constrict the path to the eardrum to provide natural attenuation. So this is kind of an attempt by your body to make it safe to listen to a wider range of dynamics in the real world, and mimicking this behavior allows us to represent a wider dynamic range of sounds within the inherently limited medium of playing sound back through speakers. So in the system, we allow you to attach a loudness value to each sound asset in dB SPL, and it can go all the way from 0 to 220 dB, although this is a really extreme range, like that would destroy your actual ears. So in the game, you really need to use anything more than like between 40 and about 150 dB to get what you need. Each instance of a HDR sound is then metered at runtime in dBFS, and a conceptual loudness in dBSPL is calculated from that. And this is used to calculate the loudness of the whole HDR system together, which by default kind of rests at 80 dB because that's where the stapedius reflex kicks in most people. Then louder sounds move the current loudness of the system up, and all of the sounds are mixed down by the difference between this level and the resting level. That's pretty simple in concept, but the complexity is how it actually gets all those metered levels. This has the effect of maintaining loudness relationships between sounds while making space in the mix for the louder sounds. This implies that there's also a positive correlation between loudness and the importance of the sound, which, conceptually debatable, but the system does this for you. It's also not a compressor or a ducking mixer for this reason, because the loudness relationships are maintained. So when we were planning this system, we took a lot of learnings about how the engine is put together from the audio inspector. So displaying something for debug purposes is a great way to learn how it works for yourself. So I'd recommend whipping something up like this if you have the time to really grasp the structure of UE audio. And we knew we needed to make use the most fundamental part of the engine's whole extensibility framework and make this into a plugin, since we knew we'd want to share this technology between projects without having to do any costly engine customization and then port that engine customization every time. But this implied that we could only implement HDR by making use of the extension points that the audio engine provides. Happily, there were many relevant extension points that can be used to implement mixing within the engine. And those that we required some tweaks and help to were supported by the UE audio team, who, as you probably know, are a very open and outward-facing group. So do get in touch with them if you need extra support from stuff. And we identified some things that HDR needed. So we needed to be able to opt sounds into the system. We wanted it to be as light touch as possible on the game, since other HDR workflows can necessitate a lot of heavy hand authoring, and they're pretty holistic. Like, you either HDR your mix or you don't. But we didn't think it had to be this way. We also needed to be able to author data individually per sound asset, so we can define loudness and other aspects of mixing for the sound, like post-gain and that kind of thing. We knew we'd need to be able to intercept a sound as it was started by the engine and do something to it, probably attach a metering something to it, and also keep track of it in our system. And the concept of HDR requires a centralized mixing system, which is scoped to the lifetime of the audio device. In other words, it exists for the whole lifetime of the game or the Pi session or the editor or whatever. We knew we'd need to apply the results of the mix calculation as granularly as possible, every audio render frame, so as to avoid audibly stepping the volume. And to handle content at scale, sound designers need to be able to group HDR sounds into categories whose values behave hierarchically to allow broad strokes mixing with fine-grained control. Now I'll talk a little bit about the prototyping process for HDR. So we tried using a meter analyzer as our first attempt, which is part of Audio Synesthesia plugin, to meter the sounds. And this was attached to the active sound during its creation callback. And we tried using the results of this per sound peak amplitude analysis to drive the system loudness calculations, which we then applied to the volume multiplier of the property of the active sound. That's the first thing we tried anyway, and it didn't work. There was a feedback loop between the metered amplitude and the volume multiplier, which caused volume thrashing for sounds that weren't the loudest in the system. And from this, we learned that active sounds don't really provide a way to control volume independently of their analysis. Along with this, we found that the meter analyzer works asynchronously and reports back at an interval in seconds, which is still really short, but the latency was too much inherent in this process, would be too much for how HDR could work as we intended it to. So our next attempt was to replace usage of the analyzer with a subclass of a source effect, inserted at the end of the effect chain of a sound as HDR starts. And it does both metering and mixing of the sound in the HDR system. This broke the feedback loop, and it was frame latent, which we considered acceptable. But nope, it didn't work properly with sounds as they attenuated over distance. So distance attenuation in this context was ignored, as source effects are applied pre-distance attenuation in the chain. And we could sense a chicken and egg situation developing slightly here. So for the third attempt, we tried to re-implement distance attenuation behavior within the source effect that we made and programmatically disable distance attenuation for all HDR sounds. And yeah, that seemed to work pretty well. And damn it, yeah. The attenuation volume is used to inform culling behavior and provide other information to the rest of the audio engine. And we found from this that HDR needs to be able to control attenuation volume and sometimes force it higher to prevent sounds with high loudness from being attenuated when they're the loudest in the system. Like if they're further away but still the loudest, they would get distance attenuation, which we didn't want. So thank goodness for the source data override audio engine plugin. If I'm not mistaken, this was designed for simulating acoustic propagation and was initially used by Project Acoustics or Project Triton, depending on who you ask. And you can use it to alter any of the properties of a running F-Wave instance, which is just an instance of the sound wave assets when they're currently playing in the engine. In our case, we're using it to override the attenuation distance property of HDR sounds only. And these are applied post-logic, but pre-render. So you don't get any problems with data being stomped, and you don't get feedback loops, because all these overrides just go away every single render frame, and you have to reapply them. So it's very safe in that regard. And this is a little cool GIF of Project Acoustics, which it was made for. And this ended up being the architecture we shipped with. This extension is really powerful because you can basically do anything to running sounds with it. So great power comes great responsibility, massive foot guns and all that kind of thing. But it's really cool. You should check it out if you want to do some mixing stuff. So next we settled on some structure for the HDR plugin. And to add HDR data to individual sound assets, we used what's called an asset user data. This is an engine-wide concept that allows you to attach your own data types to engine assets, effectively making them extensible data types without requiring you to subclass them, which is a really tedious and long process to do. Sound-based assets implement this pattern. So whoever made that decision in the engine team, thank you so much. That's awesome. This solution worked particularly well at scale as well, compared to other more centralized options like having a data table and attaching data to it that way. Because if you use game feature plugins, for example, data can disappear when they're not loaded, and then you end up with missing references in data table. Whereas with asset user data, the data is always there attached to the asset when you need it. It also uses an audio subsystem as its centralized logic point. So when you write an audio subsystem, they're automatically created at the same time as an audio device whenever the game client or Pi starts. And it also runs in the editor alongside the editor's audio device. And they tick on the audio thread, which is great news because they can directly access audio engine data and make changes in a thread-safe way. You don't need to worry about any thread concerns if you have one of these things running. It also doesn't use game thread CPU time unnecessarily, so you don't have to sustain the ire of a technical director asking for critical CPU time back on the game thread, which is great. We found that it's possible to intercept active sounds as they start by implementing the iActiveSound update interface. As active sounds are created, deleted, virtualized, and realized, they invoke the interface functions here, and your code that implements this gets notified. And so we implemented this on our HDR subsystem, which then registers the sound as it starts with the HDR system and attaches the source effect to it. And as things developed, we knew we wanted to be able to control the mix at runtime as well as let the system mix. So HDR sounds have that static loudness value in dBSPL authored for each of them, as I mentioned. However, it's always going to be the case that with a mix system, you'll need to apply dynamic changes at runtime to the mix based on the game state or mix choices, whatever. So we wanted to make sure there was a way to do this through blueprints, as you might expect, but also allowing it to be through MetaSound outputs. Since some logical calculation can take place within a MetaSound graph, you can have like a first-person or third-person switch, for example, in a MetaSound, and this can change dynamically, and you might want to alter the loudness of the playing sound based on that. So in order to do this through blueprints, you have to expose code to the blueprint editor. The easiest way to make something available to a subsystem from a subsystem to blueprints is to tag a function with ufunction, blueprint callable, which works, but you always have to then get the subsystem in blueprints before you can call any of these functions, which is like another 5 more clicks. It's really tedious. It's in danger of breaking flow, which we don't want to do. So to get around that, we created what's called a blueprint function library that wraps all of the ufunction tag functions on the subsystem inside static accessible anywhere functions, doing the tedious part of getting the active HDR subsystem in code for you, so you don't have to do it. All you have to do is just call the function that you want, like override loudness at this point, or clear loudness overrides, or whatever. The other way we gathered mix offset data was by using a MetaSound interface to allow sound designers to write offset values from inside the MetaSounds. So interfaces formalize the name of a MetaSound input or output, so you can always be sure that you're sending data to the right thing or receiving data from the right place. So in our case, it was called SweejTech.hdr.loudness modifier. You know that's going to be what you need. And this interface is listened to in the HDR subsystem when calculating individual sounds' loudness values, and the values applied additively to the static loudness for each sound, which then goes on to affect the subsystem loudness calculations. And like I said, right now, MetaSound interfaces are defined in code, kind of like this, but I believe the plan is that you'll be able to define them in project data, which would allow technical sound designers to get in on the action of using these things, which is really cool, so I'm looking forward to that. And editor side for HDR, we had several workflows as opposed to just the one for Audio Inspector. So we wanted to be able to author, monitor, and visualize the system from within these workflows. And at the core of our monitoring and authoring workflows are Slate S-list view and S-hierarchical list view widgets, which present lists and hierarchies based on any data structure that you provide, which is going to be, in this case, just an array. And with the hierarchical view, it gives you callbacks to kind of generate a hierarchy from that. This really brief explanation glosses over that they are actually quite a lot of work to implement and take a lot of time, but they're really worth it when you do. And if you do end up implementing one of these things, I'd thoroughly recommend you use a model view model pattern. A little bit more about that is in that talk I referenced earlier, Building the Audio Inspector. Again, go check it out if you want to know more. And for visualizing the system, we used an S-leaf widget to do its own custom rendering. So this was cool because we wanted to do something very bespoke that wasn't supported by the engine. We wanted to just draw all these loudness lines based on what was going on in the subsystem. To do that, there's a lot of helper code for common UI rendering tasks like draw a line between this point and that point, which we built all our stuff on. And this really all came together to build a flow that allows hierarchical mixing of HDR sounds with an inspector, monitoring, and debug tools in the editor. And along with this, we have a suite of tests that makes use of the automation test framework of Unreal Engine. And the main idea of these tests is to prevent regressions. Yeah, I know it's early, come on. It's okay. Tests are really cool. They are super awesome for making sure you don't have to worry about stuff when you're fixing problems. So there are two main kinds of tests we use to achieve this. There's unit tests, which are small code-defined tests written to check individual small parts of functionality of some code. So we use them mainly to test our math code and algorithm reliability, and sometimes do some opaque system testing down to the function or the class level. And you can run them through the automation test framework in the editor, or you can set up on the command line to run. And then there are functional tests, which are blueprints made by usually technical sound designers, which reside in some test level. And these, in our case, make use of envelope followers to track the expected level of sounds in certain contexts. So this is cool because you're kind of opaquely testing the entire system from a sound point of view. And it has the benefit of making them audible. So you can naturally test stuff with your ears by just setting it running and sitting and listening to it, as well as letting it be tested by the numbers. So that's cool, because sometimes if you're testing something, you have to manually repeat the process. You don't really necessarily want to be doing that and also trying to listen to it. So yeah, these are pretty cool. And the unit tests in particular made use of another engine extension point, which I'm really excited about, which is the MetaSound Builder API. So this allows you to create MetaSounds at runtime via C++ or Blueprint using this kind of code. And in our case, we use it just to manufacture test MetaSounds so that we don't have to include any data in plugins to support the tests. But I'm sure there are many more, in fact, I know there are many more creative uses of the MetaSound Builder API out there. The game Mix Universe is basically one massive use of this thing. And I'll leave that as an exercise for the listener to figure out all the other cool ways of using this stuff. So I've talked a long time about HDR, and now I'm going to actually play some HDR system running. So what you're going to hear is the ambiences kind of just sitting away below the resting level, and then some loud things are going to come in and blow the cobwebs off. And then you'll hear the ambiences come back in again after the system is. So let's go. It's cool because as well as hearing it with your ears, you can kind of see what's going on. And I know sound designers and audio people always need the visuals to back up what we're hearing. So we're not just did you really hear this? Yes, you really heard this. It really happened. So to recap, we used a lot of extensions in the process of creating the HDR plugin. And those are subsystems, source effects, audio analyzers. Why did I make this so fast? audio analyzers, active sound update interface, source data override, blueprint function libraries, MetaSound interfaces, and the MetaSound Builder API. So, onto the plugin we released earlier this year, Ambience. I'll start again with a little overview of what our Ambience plugin does. So at its core, the system allows you to author complex soundscapes and volumes with volumes inside a game world. It uses distance to the listener to the volume to fade ambient beds in and out, and it blends and mixes between them using a priority value that you set on the volumes. Spot sounds are scattered in around the listener based on sets of logic defined on the volumes and in assets, and reverb sends and area types parameters are blended using distance as well. So this plugin was developed initially for an in-house project at SweetJustice that is a large open world title where there needs to be a sense of scale, but also lots of intimate details of a lived-in place. And we knew we needed to have distance-based crossfading rather than time-based boundary crossfades, as this really increases tangibility and interactivity of the soundscapes. Like they really sound more real if you can feel the change as you're moving between them rather than just kind of ticking over a boundary and then hearing the change over time. So to help achieve this, we wanted to be able to swap and blend content inside MetaSound instances based on some parameters supplied automatically from the Ambience system from outside. And we also wanted to be able to blend reverb sends based on distance as well, for the same reason that we want to blend content on distance. We knew we'd need to auto-scatter those spot sounds to add depth and detail to the soundscape. And as with everything we do, it would need to be highly inspectable and debuggable so that sound designers working on the system can just see exactly what's going on at a glance. So when we were planning it, we realized it's a system that's much more gameplay audio than HDR in that it interacts with other gameplay systems and level design features of the engine at a much sort of higher level. And as a result of this, some of the system is made from parts of the gameplay framework, or in other words, from actors and actor components. And it follows from this that it has to exist in the game world with a capital W and be spatial and volumetric in nature in a way that HDR was not. We also realized we'd need to create asset types to manage the complexity of this system and make use of them at runtime in various different contexts. And so we'd probably need to work with some different extension points, along with some familiar ones that we knew from HDR. So the first iteration of the system in our prototyping process was made completely in blueprints with actors and components. And there was a manager blueprint spawned by the game mode, which acted as a centralized system and arbitrator for distance and priority. It worked as a proof of concept, but there were some problems, of course. So it only supported primitive shapes because we had to do them with just pure maths and code. And there was no ability to share instances of sounds between volumes. We realized that if you have two overlapping volumes with the same ambience bed, there's basically no case in which you want two versions of that ambience bed to be playing at the same time. We couldn't do that in our first setup. So for a second iteration, we made use of the brush system for defining volumes. So we had to move all of our logic and code stuff to C++ to make use of this. And also for performance reasons, because in general, stuff in C++ runs better. You don't have to hit the virtual machine of the blueprint. We also created a subsystem to replace the blueprint manager to ensure that lifetimes of objects are handled correctly and that the subsystem was accessible from anywhere at any time it would need to be. This unlocked a lot of usability and made less busy work for sound designers, but it didn't scale very well into the hundreds of volumes, or even thousands that sometimes we ended up needing. Also because each volume did its own spatial calculations, which was not great for performance at all. So for the third iteration, we moved spatial logic and playback logic into the subsystem, which meant increased performance for large volume counts and the ability to share instances of sound between the volumes. And the actors and components themselves were slimmed down to basically only be data carriers and spatial markers for what was going on in the world. And there were no problems with this. No, just kidding, there were problems, but basically the setup for the system was a really good fit for our goals, so we kind of left it there. And here is how crossfading over distance sounds in the system. So what you're going to hear is the ambience of the sort of lake and the trees and stuff, and some birds in the trees. And as you get closer to the house, it's going to crossfade into the house air tone, and some of the ambience surrounding it will be pulled down. Bit more subtle than the last one. So area types are our way of crossfading pre-authored wave content based on a location or proximity to a volume. And we attach content and parameter values to area types using an area type preset asset, which is an asset type that we made ourselves for this purpose. And we define the actual area types themselves using a subclass of a user-defined enum asset. And these allow you to specify enum values in data, which allows sound designers to customize them for each project. Like the concept of an area type is going to be different pretty much for every project that you have. So we wanted to support that. And this concept coexists with MetaSounds. In fact, it's pretty much MetaSound native. So this meant we needed to make new nodes, and we needed to make new interfaces. So that was fun as a programmer. MetaSound nodes are a really powerful way to customize the engine to your needs, since you get direct access to the signal data stream if you want to, and they can be placed anywhere inside a signal chain inside a MetaSound. So when you're making one in code, you define an operator and a facade for the node. You define the vertex inputs and outputs. These are the little pins that you see on all MetaSound nodes that exist already and that you connect to in the editor. And then the operator itself does all the work. It has the execute callback where the logic or the DSP code runs, and it also then connects all of its inputs and outputs to readers and writers. And there's also a node facade for the editor, but it's basically just there to make it look pretty. So there are some nodes that have visualizations on them. This is where you do that. Otherwise, it's just generally a bit of boilerplate code that you have to do. So we made a few nodes for the plugin in order to implement content switching. Firstly, the get area type wave assets node, which is a bit of a mouthful. So it takes an area type ID, which is basically just an int value that comes into the MetaSound, which is defined by the area type enum as an input parameter, plus an area type preset asset, which we've already made, which maps together wave data and area types for any given purpose. And it outputs the set of wave assets mapped to the area type given as an input, which you can do whatever you want with. You can choose them at random or play them however, basically. And it's pretty simple in that regard. And typically, we use two of these in the same MetaSound patch or source effect to achieve the blending effect. The asset data that I mentioned has to have a proxy defined for it to prevent unthread-safe access to UObjects in the audio mix render thread. So you have to make an audio thread version of the data to pass in, which is a bit of a boast in terms of code, but of course it's worth doing to get your own custom data types in nodes in MetaSounds. And to go alongside this, we have the get area type parameter node that comes in the three flavors that we support of data parameters, float, int, and bool. And it's the same as before. It takes in an area type ID and a preset asset, but also the name of the property you want to extract from this thing. And it outputs the value specified in the property for that particular area type. So again, it's pretty conceptually simple. And as before, these are usually used in pairs in order to crossfade between the two area types smoothly. But the crossfading itself is again deferred to the technical sound designer to figure out how to do, because like, how do you crossfade between bools? Not sure, you've got to figure that out. So to feed these nodes the right data from the system, we needed to create an interface. And as with the HDR plugin, to create an interface, you define that interface version in code, along with its inputs and outputs, and then you register it with the module. And that's pretty much it for creating an interface. It's up to you how to feed it data, and you have to figure out how to do that yourself. So in our case, we feed it data from the ambience subsystem directly. And we implemented a listener area type MetaSound interface, which outputs a primary and secondary area type, and their mix values, which sound designers can use to mix the outputs of the aforementioned MetaSound nodes. So the values coming in through this interface ID are, this interface are IDs and mix values between 0 and 1, and they're calculated and fed by the subsystem. So in general, if the primary mix is 0.75, then the secondary mix is always going to be 0.25, if indeed there is a secondary area type. So they're always going to allow you to do that crossfading. You don't have to worry about whether they're correct. And this is an example of how we use area type crossfading. So gun in game again, so prepare your ears. But this is someone firing a gun in an outdoor area, which is going to sound always different to a sort of tunnel or small area. And with guns and percussive sounds in general, it's better to record the tails in a real environment. It sounds much better than running it through a convolution reverb. So this allows you to make use of that kind of natively in the system. So yeah, nice nice and smooth. And we also needed to, if you do want to use convolution reverb, we knew we needed to be able to blend the reverb smoothly over distance for this system to hang together coherently. And more specifically, we needed to blend the output of an effect chain. So initially, we explored requiring 2 submix buses for reverb blending. But the attenuation settings structure only allows for specifying 1 reverb send, fair enough. And we couldn't work out a way to programmatically crossfade between 2 without resorting to have a fade over time. So to get around this limitation, we settled on creating a custom SweejTech submix effect for doing this, which this is an effect that can only exist on submixes. And internally, this instantiates and renders 2 submix effect chains internally, and the subsystem provides the crossfade information for how to mix these together. And these can actually contain whatever the sound designer likes, although we advise it to be reverb, but you can have like slap delay or compressor or whatever. It's because it's an effect chain, you can do what you like. And this is a note about making your own systems extensible, because I love extensibility so much, I want to also allow it for our own stuff. So the ambience subsystem doesn't deal with ambience volumes directly. Instead, it talks to script interfaces that wrap the ambience volumes. So these are really useful if you want to allow your technical sound designers to provide behavior for the systems you build, or other coders to do that as well. So the supplied ambience volume type just implements this interface and works as you would expect out of the box, and you never need to know about it if you're just using the system. However, it also allows licensees to provide behavior for more game-specific situations. So this actually came out of one of our licensees was using it for destructible buildings, and we didn't know how the destructible building system worked, and I don't think they knew at the time either. So we just sort of gave them the tools to provide their own information about how close you were and how open the building was. So this it can also be used in your own game if you have diverging behavior over how volumes can be defined over different parts of the game. Like, for example, if you want to have a cloud, what does it mean to be close to a cloud? You can't really define that using a brush or whatever. So you can do that with more complex behavior if you want. So these can be implemented in C++ or blueprints, which also allow technical sound designers to do logic, which is really cool. And if you want to use this in blueprints, there are a couple of hoops that you need to jump through, so I'll go through it here. You need a U-type class that inherits from a U interface, and they need to be tagged with U interface, and you need an I-type with a matching name that you can see below, and you need to use the T-script interface to get the blueprints to recognize it as a parameter when you make this thing. So these 3 hoops you jump through, but once you've done that, you've unlocked one of the secret superpowers of collaboration in the engine, because you can give people the ability to provide their own behavior that wouldn't necessarily have the opportunity to do that. So it's really cool. I recommend you take a look at it if you're designing systems that tech sound designers are going to use. And another kind of like slightly boring note, but I think it's really important, is we did a lot of iteration on serialized data types in this plugin. And we made use of custom data versions to ensure there was compatibility between different versions of the data. So we deployed the plugin in multiple different projects as it was being developed, and the data changed shape multiple times throughout development. So we're really glad that we implemented this straight off the bat, because we knew we'd never had problems with data loading. And you can use it to guarantee compatibility by overriding the serialize function and calling the custom version function. If your data changes, you can add a new version to the enum that's defined in the custom data version and translate old data versions of the data into new versions when the serialize function is loading. You basically just take the old data and put it into the new structure and code. So I'll talk a little bit about the editor workflows that we made for ambience as well. We have the ambience inspector and scatter spot inspectors, which are very similar to how the audio and HDR inspectors work, but with some cool countdown bars in the rows to visualize playback time. These were made with a custom S-Leaf widget as well. And also the scatter spot inspector is a 1-level hierarchical list view, which you can see the asset at the top that defines the scatter spot, and then all the different sounds that are playing based on that, and how long until they next play. For the area type preset editor, which maps area types to wave sets and parameters, we created a detail customization. This is effectively a whole custom asset editor, which took the data type from what is a heavily nested structure hierarchy. I mean, I'm sure you've seen a bunch of these before. When the data type gets quite complex, it can just be a real mess of nesting. And then afterwards, it's a nicely laid out table view, which also did some data input validation on certain properties to make sure you're editing things correctly. We made a world selector combo box because it came as a bit of a surprise to us that when you're running Pi, there's also an editor world still running in the background, and you need to make sure you're showing the right world data. So this just made it absolutely explicit which one you are looking at a particular time. And the ability to debug render brush shapes at runtime did not exist in an accessible way, certainly at the point in time when we were making this system. So we actually borrowed and utilized the lightweight rendering technology contributed to the engine by CD Projekt Red, so thanks if anyone's listening to that. And as a bonus, because we use subsystems to do all the logic for this stuff, we can run the system in the editor viewport, which allows you to audition the ambiences and fly around without having to run Pi, which can save a huge amount of iteration time, especially if Pi loading times are taking a long time to get started. So to round up, the extension points we used for ambience were actors and components, subsystems, bus effects, blueprint function libraries, MetaSound interfaces, MetaSound nodes, and script interfaces. So now I'll go through some ongoing work and the extension points that we are exploring there. Our MetaSound interfaces plugin is a utility plugin to provide automatic interface population to individual MetaSounds. And this means for anything supported, you just add the interface to a MetaSound, and it provides the data without having to hook it up in blueprints, which can save a huge amount of time and kind of tedious work. So we make use of this for getting physics information to MetaSounds, and it is also used by our other plugins. For example, the ambience plugin uses it under the hood to send area type mix info from the subsystem to any MetaSounds that use this stuff. And to do this, it makes use of a subsystem and, of course, MetaSound interfaces to do that. And this is more or less how it would look in a MetaSound if you're adding this stuff. We also have a global parameters plugin, which, as you might expect, makes parameter values globally available, including in MetaSounds. Sound designers define the parameters and write them from Blueprint, or they can be written directly from C++. And we allow them to be read in MetaSounds via an interface. So in order to do this, this one makes use of a subsystem, MetaSound interfaces and nodes, and a Blueprint function library. And we're also working on an extremely fast convolution reverb, which you can use to save CPU time on the reverb that you are currently using. You could just use more reverb. Maybe that's a little bit overkill. But, you know. To do this, it uses the reverb audio engine plugin extension point, which is inside the iAudio extension plugin header file. So there's a whole bunch of really cool extensibility things that are inside this header file. It's like a gold mine in there. So if you're a coder, or not even, just go open up the editor and take a look in that file. And that's like where you can really do some powerful stuff with extending the engine. And finally, this last one is still really experimental to us, but we're exploring how to use GPU ray tracing to simulate acoustic propagation phenomena in UE5. I would have put a video in this, but we've posted something about this on social media, but yeah, go check it out if you want to. So to do this, we're making use of the render graph interface, which allows you to schedule ray tracing and compute shader jobs on the GPU. Sorry, not sorry, rendering programmers. It means we've had to get into shader writing as well, which is totally a weirdly foreign land for us as audio programmers, but it's very cool and super powerful, especially if you want to do stuff with many, many instances of sounds. And then once we've got that ray tracing information about the scene, we plug the results of this together with the occlusion plugin, which we found in iAudio extension plugin header file to simulate obstruction and occlusion based on the results of the ray tracing and some other cool processes that we're going through. So yeah, we'll talk more about this as it starts to come together. So to round off the talk with some takeaways, there are numerous well-defined extension points to the Unreal Audio engine and other parts of the engine you might want to use to develop audio tech. They can be plugged together for a force multiplier to build complex systems that scale from small bespoke projects to gigantic hulking mega games. They can be used to make project-specific behavior that it wouldn't make sense to share, but they can also be built into the plugin architecture of Unreal Engine and shared between projects, or made available through open source or fab or however you share your work. And finally, the extensibility of Unreal Audio Engine allows you to express your creativity and ideas in a way that I haven't really encountered in other engines and audio tech packages, which is why, in the end, we spend so much time building with it and why I was here talking to you about it today. So, Thank you very much, and please ask questions.